geometrical representation of algebra of complex numbers. In this module, you will learn the geometrical representation of algebra of complex numbers. To represent conjugate of a complex number, consider a complex number a plus iota b in the argand plane. Its conjugate a minus iota b is represented by the coordinates a minus b in the argand plane. Notice that the conjugate of a complex number is the image of complex number itself on the real axis. Every complex number possesses magnitude as well as direction. The modulus of a complex number represents its magnitude, while the argument represents its direction. Such quantities having magnitude as well as direction are known as vectors, and they are represented by directed line segments. Now, we will use this concept of vectors to represent addition of complex numbers geometrically. Consider two complex numbers x1 plus iota y1 and x2 plus iota y2 in the argand plane. To find the sum of these two complex numbers, draw a parallelogram OPRQ in which OP and OQ are the adjacent sides. If a particle is displaced from O to P and then to R, the final position will be the same if it were displaced from O to R. Thus, vector OR is equal to vector OP plus vector PR. Since opposite sides of a parallelogram are parallel and equal, these two sides will also be parallel and equal. Two vectors are said to be equal if their magnitude and direction are same wherever they are located in the space. Hence, these two vectors are also equal. This helps us to derive that vector OR is also equal to the sum of the vectors OP and OQ. Now, draw perpendiculars from P, Q and R on real axis. Also, draw a perpendicular from point P on RM as shown. Notice that these two triangles are congruent. So, their corresponding sides are equal. This helps you conclude that these three line segments are equal and their length is x2. Similarly, these two vertical line segments are equal and their length is y2. Now, sum of these two horizontal distances on x-axis gives the x-coordinate of point R, and the sum of these two vertical distances gives the y-coordinate of point R. Thus, coordinates of point R are x1 plus x2 and y1 plus y2, or you can say vector OR represents the complex number x1 plus x2 whole plus iota y1 plus y2 whole. This discussion helps us to derive that the sum of the complex numbers is the sum of its real parts and the sum of their imaginary parts. Now, to find the difference between two complex numbers, again consider these two complex numbers in the argand plane. The difference of these two complex numbers is same as adding the first complex number and the negative of second complex number. Vector OQ dash, having same magnitude but opposite direction to vector OQ, represents the negative of complex number x2 plus iota y2. Notice that vector OR represents the sum of vector OP and vector OQ dash, or you can say vector OR represents the difference of vector OP and vector OQ. Thus, coordinates of point R are x1 minus x2, y1 minus y2. So, this helps us to arrive at the fact that the difference of two complex numbers is the difference of their real parts and the difference of their imaginary parts. Next, to find the product of two complex numbers geometrically, consider two complex numbers with polar coordinates r2 theta and r1 beta in the polar plane. Now, draw a triangle OAL such that OL lying on real axis has unit length. Also, construct another triangle OBP similar to this triangle such that OA and OP are the corresponding sides of these triangles. Since these two triangles are similar, the ratios of corresponding sides of these triangles are also equal. Solving this equality of ratios for OP, we get OP is equal to R1 R2. Also, angle POX is equal to theta plus beta. Thus, P is the point whose modulus is R1 R2 and argument is theta plus beta, and it represents the product of these two complex numbers. So, polar form of complex number represented by vector OP is R1 R2 into cos theta plus beta plus iota sin theta plus beta whole. Now, to see the geometric representation of division of two complex numbers, consider again two complex numbers with polar coordinates r1 alpha and r2 beta in the polar plane. Draw triangle OBL such that OL lying on real axis has unit length. Also, construct another triangle OAP similar to this triangle. The ratios of corresponding sides of these two triangles are equal. This fact helps us to derive that OP is equal to R1 upon R2. Also, angle POX is equal to alpha minus beta. So, polar form of complex number represented by vector OP is R1 upon R2 into cos alpha minus beta plus iota sin alpha minus beta whole. This point P gives the division of complex numbers represented by points A and B. In this module you have learned that conjugate of a complex number is the image of complex number itself in the real axis. The sum of the complex numbers is the sum of their real parts and the sum of their imaginary parts. The difference of two complex numbers is the difference of their real parts and the difference of their imaginary parts. The product of two complex numbers with polar coordinates r1 theta and r2 beta is r1 r2 into cos theta plus beta plus iota sin theta plus beta whole. The division of two complex numbers with polar coordinates r1 alpha and r2 beta gives r1 upon r2 into cos alpha minus beta plus iota sin alpha minus beta whole.